So we know that an action potential is all or nothing, but what if we want a stronger signal? Right? What if, let's take sensory from our sense of touch, from our tactile corpuscles in our skin. Well, if something lands on our skin, we know if it's lighter or heavier, if it's producing more, a stronger stimulus or a weaker stimulus. So how does our brain know that a stimulus is stronger or weaker if the action potential on that given pathway, those action potentials are always the same strength? So another way to ask that, how do you code for a stimulus? How does the brain know there's a stronger stimulus or a weaker stimulus? And the answer would be, or is, frequency. So you have more action potentials or less action potentials in a given period of time. So the higher frequency of an action potential means a stronger stimulus. And this is hard to picture with words, so let's look at the picture on the next slide. So here, let's just say something extremely tiny lands on your skin. It produces a stimulus, but it wasn't enough to reach threshold. So are there any action potentials to your brain? Well, no, because that tiny little microorganism that landed on your skin that produced little response, graded potentials, was not enough to reach threshold, and we were never aware of that happening because the brain didn't receive any information. But let's say a tiny little, let's say a mosquito lands on your skin. Well, it's strong enough, there's our threshold of what we can feel. It was strong enough that signals were sent to the brain. Looks like we have 4 action potentials, and that tells the brain that, yeah, it's a given intensity of pressure on my skin that mosquito landed on. So I'm feeling it, and this tells the brain how strong that stimulus, that sensation of touch is at that spot on my skin. But let's say something heavier. Let's take I don't know what's something, a larger insect, or let's just say a ball hits your skin, much stronger than if a mosquito hit it. Well, there's what your brain's receiving. We're receiving action potentials, but they're a lot closer together, and there's so many of them within a short period of time. So it's telling our brain, well, yeah, this is a much stronger stimulus, has more intensity than that mosquito. So you can see the space in between the action potentials. This is an extremely short amount of time, right? Same here, but your brain is receiving a lot more action potentials here. So that's what frequency of action potential means. And if you look at the height of these action potentials, they're all identical, right? They either happened or they didn't, right? And even though the action potentials are identical in both stimuli, there's just more of them here, kind of crammed into a small amount of time. And that's how we code for intensity. That's how we tell our brain what stimulus is stronger or which stimulus is less intense based on the frequency of action potentials going towards the brain. There are two refractory periods, an absolute refractory period on this slide and a relative refractory period on the next slide. I'm going to just briefly go through both, but I'll spend a little more time on the picture after these 2 slides to kind of further the point. So an absolute refractory period means you cannot have another action potential. Sodium channels are still open during repolarization, so it's impossible to respond to another stimulus. So basically what an absolute refractory period means, it's impossible to have another action potential because the channels have not been reset yet. A relative refractory period means it's difficult to produce an action potential, but it is possible, but you would need, like it says, an exceptionally strong stimulus that can produce an action potential. So on the previous slide, absolute refractory period is an impossible situation to produce an action potential, where a relative refractory period can produce an action potential, but the stimulus has to be extremely strong. All right, so now let's go to the picture on the next slide and we'll explain both. So you see in kind of the greenish gray color here, this is depolarization, right? There's your resting state, there's your depolarization. So during this area in yellow, all the way up to about there, the sodium channels are open and then they start closing. So since the sodium channels are open and depolarization is happening, sodium's rushing in, that's where our action potential is beginning. It's impossible to have another action potential right here because it's already producing one. Right? So during this period of time, that's called the absolute refractory period, during this period of time from 0 to 1 microseconds or whatever it is, it's impossible for another action potential to begin because the sodium gates need to reset first. They're still open here. They haven't even closed yet. So no way another action potential could begin. Right? But then if we go to the next area, which is this darker blue area right here, we can see during most of this time we have hyperpolarization, meaning, well, resting state is -70, but it's less than the resting state. And since, let's just say it's -80, which makes it further from positive, further from zero at least, than in the resting state. So we know we can produce an action potential, right, from the resting state, but if the neuron is hyperpolarized, you still can. It's just going to take more work, this much more work right here. Right, so an action potential is possible. It's just more difficult because we need a stronger stimulus to get there than we did if we were at rest right here at -70. So the relative refractory period means, yes, of course, an action potential is possible. We just need a stronger stimulus than normal to get there. Or absolute refractory period, no possible way another action potential can be produced.